What if Mars once had beaches just like Earth, waves crashing, tides rising, and shorelines stretching for hundreds of miles? Imagine standing on a red coastline under a sky lit by not one, but two moons. For decades, scientists argued over whether this was real or just a mirage in the data. But then came China's Zhurong Rover, armed with tools no one had ever used on Mars before. And what it uncovered could change everything we thought we knew about the red planet. Imagine standing on a shoreline bathed in crimson dust, the Martian sun setting behind distant hills. Gentle waves of a long-lost ocean lap against your boots, and for a moment, it feels like Earth. But then you look up and notice not one, but two moons, Phobos and Deimos, glowing in the twilight. Suddenly you realize you are not home. You are on Mars. This vivid image is no science fiction. It's the kind of scenario scientists now believe could have been real billions of years ago. For decades, researchers debated whether Mars once held vast oceans. Some claimed the evidence was too weak, while others pointed to valleys, minerals, and ice as clues of a watery past. Yet, the mystery remained unresolved, shrouded in doubt. The idea of Martian shorelines was often dismissed as a mirage, a trick of geology and wishful thinking. That was until an unexpected player entered the scene. In 2020, China launched its most ambitious interplanetary mission, setting out to challenge the giants of space exploration. While NASA and ESA had long dominated the red planet, a new rover named Zhurong carried with it the promise of rewriting history. Equipped with tools no one had ever used directly on Martian soil, it was ready to search for answers buried beneath the dust. And the results? Nothing short of astonishing. What Zhurong uncovered beneath the Martian surface has the power to silence skeptics forever. For the first time, solid ground evidence supports the existence of ancient oceans, vast stores of hidden ice, and even signs of recent geological activity. Together, these findings reshape our vision of Mars, not as a barren rock, but as a planet that once breathed with potential. In this journey, we'll dive into 3 unbelievable discoveries made by the Zhurong Rover. Each one challenges what we thought we knew. Each one draws us closer to answering the ultimate question. Could life have once thrived on the shores of Mars? The Tianwen Trucreao. One mission. The story begins with Tianwen-1, China's bold step into Martian exploration. Launched in July 2020, the mission was far more than a simple flyby or orbiter. It was a complete package, an orbiter, a lander, and a rover, all launched together in one mission. If successful, China would not only orbit Mars, but also land and deploy a rover, something no other nation except the United States had ever achieved. After a 7-month journey across deep space, Tianwen-1 entered orbit around Mars in February 2021. For months, it circled the planet, scouting potential landing zones and testing its systems. Engineers adjusted its orbit, shifting it from equatorial to polar, ensuring the perfect trajectory for descent. All the while, the world watched. Could China pull off what had taken NASA decades to master? On May 14, 2021, the answer came. The lander touched down safely on Utopia Planitia, a vast plain once suspected to be the site of an ancient ocean. A week later, the rover Zhurong rolled onto the Martian surface, becoming the first non-American rover to operate on Mars. With this success, China instantly established itself as a major player in interplanetary science. The mission's objectives were clear but ambitious: study Martian geology, monitor its climate, and search for signs of water and habitability. More importantly, Tianwen-1 was a proof of capability. It demonstrated that China could launch, navigate, land, and operate on Mars independently without relying on foreign navigation systems. For the Chinese space program, this was more than science. It was a statement of technological maturity. Armed with 13 scientific instruments, including ground-penetrating radar, spectrometers, cameras, and meteorological sensors, Zhurong was ready to dig deep into Mars's secrets. And as it began to scan the soil and rocks of Utopia Planitia, it uncovered the first of its breathtaking discoveries, evidence of a long-forgotten shoreline. The role of the Zhurong rover. At first glance, Zhurong might look like a cousin of NASA's rovers, but this little explorer had its own unique arsenal. Weighing about 240 kilograms, it stood smaller than Curiosity or Perseverance, yet packed with innovation. Its design balanced mobility with scientific power, making it perfectly suited to investigate Utopia Planitia, the largest impact basin in the solar system. One of its most important tools was the ground-penetrating radar. This instrument could peer up to 100 meters beneath the Martian surface, detecting hidden layers of rock, sand, and possibly ice. No rover before had provided such direct subsurface imaging on Mars. Alongside this, Zhurong carried spectrometers to analyze the composition of rocks and soil, cameras to map terrain in exquisite detail, and a weather station to record wind, temperature, and pressure. But Zhurong wasn't just about science, it was also a symbol. For China, deploying a rover on Mars demonstrated a leap in independence. Unlike earlier missions that depended on global navigation networks, Tianwen-1 operated fully on its own. Every image transmitted back to Earth, every radar pulse sent into the ground, reinforced China's growing reputation as a space power. Its landing site, Utopia Planitia, was carefully chosen. Decades earlier, NASA's Viking 2 had landed in the same region, but with limited technology of the 1970s. Scientists had long suspected that this plane, once shaped by massive impacts, might have also hosted ancient oceans. With Zhurong, they now had the tools to test that theory from the ground. For nearly a year, the rover rolled across the Martian dust, transmitting not just photos, but insights into the very history of the planet. And soon, it delivered its first astonishing result: evidence that the dusty plain it explored was once kissed by Martian waves. The first major discovery: evidence of ancient oceans. Zhurong's radar sent pulses deep into the soil of Utopia Planitia, bouncing signals back whenever it hit a boundary between different materials. What stunned scientists wasn't just the echoes, it was the angles. Dozens of layers beneath the surface sloped consistently in the same direction, between 6 and 20 degrees. This wasn't random, it was a fingerprint. On Earth, such inclined layers are common along coastlines. They form where waves, tides, and currents deposit sediments over long periods, creating a gentle tilt as new material builds up. The comparison was striking. When researchers placed Zhurong's data side by side with coastal records on Earth, such as the Bay of Bengal, they found uncanny similarities. It was as though Mars had recorded its own shoreline diary, preserved under dust for billions of years. If correct, this discovery was groundbreaking. For the first time, scientists had direct, on-the-ground evidence of a Martian coastline. It wasn't just satellite images hinting at patterns or theories based on erosion. This was a rover confirming that Mars once had an environment shaped by water as dynamic as Earth's beaches. The implications were enormous. Coastal environments are hotspots for chemical activity, ideal for concentrating organic molecules and fostering the chemistry of life. If Mars ever hosted primitive ecosystems, ancient shorelines like the one in Utopia Planitia could have been the perfect cradle. Skeptics had long dismissed Martian ocean theories as overinterpretation. But Zhurong's findings forced the debate into a new light. This wasn't illusion or coincidence. The evidence pointed toward waves, tides, and rivers feeding into a body of water vast enough to be called an ocean. And with it came the thrilling possibility that life once flourished along Mars's now buried shores. Comparison with Earth's beaches. To fully grasp the importance of Zhurong's findings, it helps to look at Earth's own coastlines. On our planet, beaches form where sediments carried by rivers, glaciers, or winds eventually settle in calmer waters. Over time, waves and tides sort these particles, creating layers that tilt gently toward the sea. These inclined strata are like fingerprints of ancient shorelines, preserved for millions of years in the geological record. The angle of these layers depends on the type of sediment. Fine sand produces shallow slopes, while coarse pebbles can stack into steeper inclines. On Earth, such slopes rarely exceed 20 degrees, exactly the range Zhurong detected on Mars. The match was too precise to ignore. Geologists immediately recognized the pattern. This was not a random deposit, but a coastal structure. This discovery connected Mars to a process we know intimately on Earth. It suggested that, like our planet, Mars once had the right combination of energy, waves, currents, and tides, shaping its landscape. Even more striking, Mars' moon Phobos could have played a role similar to our moon, generating tidal forces in its ancient oceans. For scientists, this was more than geological curiosity. It was a potential roadmap for finding biosignatures. Coastal regions on Earth are rich in organic chemistry, providing natural laboratories where molecules concentrate, react, and evolve. If life ever sparked on Mars, its beaches could have been among the best places to search for traces of it. By aligning Mars's hidden layers with Earth's familiar coastlines, Zhurong offered a powerful message. The red planet may not have been so alien after all. Its past might have mirrored ours more closely than we ever imagined. The second discovery: subsurface ice in Utopia Planitia. While scanning beneath the Martian surface, Zhurong's radar revealed another astonishing secret: vast reserves of frozen water hidden underground. Scientists estimated that Utopia Planitia contains as much ice as Lake Superior, one of Earth's largest freshwater lakes. That's about 12,100 cubic kilometers of frozen water, an incredible resource lying just meters below the soil. This finding confirmed earlier suspicions raised by NASA's orbiters in 2016. But Zhurong provided ground truth, verifying that Mars still holds enormous amounts of ice in accessible regions. For planetary scientists, this discovery was critical. For future explorers, it was priceless. Ice means water to drink, oxygen to breathe, and even hydrogen for rocket fuel. It is the cornerstone of any long-term human presence on Mars. Beyond its practical value, the ice also tells a story about Mars's past climate. Large underground reserves suggest that Mars once experienced cycles of freezing and melting, perhaps driven by shifts in its orbit or tilt. Such cycles could have supported temporary periods when liquid water flowed, carving valleys and filling lakes. But there's an even more exciting implication: preservation. Ice can trap and protect ancient organic molecules, even microbial life, for billions of years. On Earth, scientists have revived microbes frozen for tens of thousands of years. Could Mars's icy vaults hold similar secrets waiting to be uncovered? By uncovering both ancient shorelines and modern ice, Zhurong painted a picture of Mars as a planet with a dynamic water history. Not only had it once hosted oceans, but it also continues to guard massive reservoirs beneath its frozen deserts, remnants of a wetter, more hospitable world. The importance of water on Mars. Water is more than just a liquid. It is the foundation of life as we know it. On Earth, it covers over 70% of the surface and shapes every ecosystem. From rivers and oceans to the cells within our bodies, water is the universal solvent, enabling the chemistry of life to flourish. That is why every space mission, from Mars rovers to distant probes, has followed one golden rule: find the water, and you might find life. On Mars, the hunt for water has been ongoing for decades. Ancient riverbeds, dry deltas, and polar ice caps already hinted at a wetter past. Minerals such as hydrated salts and ferrihydrite further confirmed that liquid water once interacted with Martian soil. Yet, most of this evidence came indirectly, from orbiters and meteorite studies. What Zhurong provided was a rare chance to verify it on the ground. The presence of ancient shorelines combined with underground ice transforms our view of Mars from a barren desert into a world that may once have been rich in habitats. Coastal regions, in particular, could have offered the perfect conditions for early life. On Earth, these zones concentrate organic molecules, provide mineral surfaces for chemical reactions, and harness energy from tides, heat, and sunlight. In contrast, rivers are too dynamic and dilute for life's fragile chemistry to persist. They constantly wash away molecules before they can accumulate. Oceans and coastal shelves, however, allow for stability. They create environments where RNA, proteins, and other building blocks of life can form, evolve, and potentially thrive. This is why Zhurong's findings matter so deeply. They don't just reveal Martian geology, they point directly to potential habitats. And if life ever took hold on Mars, the fingerprints may still be preserved in these watery archives. The third discovery: signs of recent geological activity. Zhurong's data didn't only reveal ancient oceans and frozen reservoirs. It also hinted at something more surprising: signs that Mars might still be geologically active. Beneath the dust, researchers detected structures suggesting recent movement, such as shifts in layers and changes in the subsurface terrain. This contradicted the long-held belief that Mars has been geologically dead for billions of years. If true, this means Mars may still have processes shaping its surface today. Small-scale quakes, shifting sediments, or even localized volcanic activity could be ongoing. These subtle movements matter because they influence how ice melts, how gases escape into the atmosphere, and how habitable environments might temporarily appear. On Earth, geological activity is a key ingredient for sustaining life. It recycles nutrients, creates energy gradients, and maintains climates. If Mars retains even traces of this activity, it strengthens the possibility that conditions for microbial survival could exist below its surface. The radar data suggested that some subsurface layers were younger than expected, with angles too uniform to be ancient. This raised questions. Could groundwater have reshaped the soil more recently? Could volcanic heat have melted ice, creating temporary pockets of liquid water? Both scenarios would make Mars far more dynamic than previously thought. Though still debated, these findings expanded the mission's impact. Zhurong was no longer just uncovering the planet's distant past. It was hinting at a living planet, still evolving in subtle but important ways. For scientists, this was a game changer, sparking fresh interest in exploring not only Mars's history, but its present-day potential. The faint young sun paradox. One of the greatest mysteries of planetary science is known as the faint young sun paradox. Billions of years ago, when Mars supposedly hosted oceans and rivers, the sun was about 25% dimmer than it is today. With so little energy reaching the planet, Mars should have been locked in deep freeze, incapable of sustaining liquid water on its surface. And yet, the geological evidence tells another story. Scientists have wrestled with this contradiction for decades. If the sun wasn't strong enough, then something else must have warmed Mars. A thick atmosphere rich in greenhouse gases like carbon dioxide, methane, or hydrogen could have trapped enough heat. But climate models show that even with enormous amounts of CO2, the warming effect still falls short. Other gases, such as methane or ammonia, might help, but they are chemically unstable and unlikely to persist for long periods. Zhurong's discovery of ancient shorelines adds more weight to this puzzle. The evidence of oceans is now stronger than ever, yet our models cannot fully explain how they could have existed. This forces scientists to reimagine Mars's climate, exploring combinations of greenhouse gases, volcanic activity, and even temporary warming events caused by asteroid impacts. The paradox isn't just academic. If we solve it, we'll learn more about the conditions that allow planets to remain habitable, even when their stars don't provide enough energy. This knowledge could help us identify which exoplanets might sustain life, despite orbiting faint or unstable suns. For now, the paradox remains unsolved. But with each new discovery, like Zhurong's evidence of shorelines, we inch closer to unraveling the riddle of how a cold, dim world once supported vast oceans. Theories about Mars' past climate. To explain the paradox, scientists have developed three main theories about Mars's ancient climate. The first suggests that Mars was warm and wet. In this scenario, a thick atmosphere loaded with greenhouse gases kept temperatures above freezing for millions of years. This would explain the presence of rivers, lakes, and oceans, but as models show, it's nearly impossible for CO2 and water vapor alone to generate enough warming. The second theory imagines Mars as cold and icy for most of its history. Here, glaciers and snow covered the planet, but occasional bursts of warmth, caused by volcanic eruptions or asteroid impacts, melted the ice. During these short-lived periods, liquid water flowed, carving valleys and filling temporary lakes. The problem with this theory is scale. Could such brief warming events really account for the massive landscapes of erosion we see today? The third theory proposes a mixed climate, where Mars oscillated between warm and cold phases. These shifts could have been triggered by changes in its axial tilt or orbit, producing cycles of melting and freezing. This scenario fits well with the presence of both glacial features and fluvial channels. However, it still leaves questions about how stable oceans could have lasted long enough to form shorelines like those Zhurong detected. Each of these models has strengths and weaknesses, and none perfectly fits all the evidence. That's what makes Zhurong's discovery so important. They push scientists to refine these theories, to reconsider the atmospheric chemistry, and to test new models. The challenge now is not only to explain how water once flowed, but also to understand why it vanished. Mars's past climate remains an unsolved puzzle, a story written in layers of dust and ice, and Zhurong has just handed us new chapters, urging us to read deeper. The mystery. What happened to all of Mars' water? If Mars once had vast oceans, rivers, and glaciers, the natural question is, where did all the water go? Today, the planet is dry, its surface carved with scars of a wetter past, but with almost no liquid water in sight. Scientists believe the answer lies in a combination of processes that slowly stripped Mars of its oceans. One leading theory suggests that much of the water seeped underground, locked as ice in permafrost or absorbed into hydrated minerals. Another possibility is atmospheric escape. Without a strong magnetic field, Mars was vulnerable to the solar wind, which gradually blew away its atmosphere and allowed water vapor to escape into space. Over billions of years, this could have drained much of its reservoirs. Some water still remains, of course, frozen in the polar ice caps and hidden beneath regions like Utopia Planitia. But the sheer scale of missing water is staggering. If we could somehow melt all of Mars's known ice, the planet would still only have a shallow ocean compared to what evidence suggests once existed. This mystery has profound implications. Understanding what happened to Mars's water helps us predict the fate of other planets, even Earth. Could the same processes that stripped Mars eventually affect us? And if water still lingers underground, could it shelter microbial life, preserved in icy pockets safe from radiation? The search for these answers is ongoing. Every rover, orbiter, and lander contributes another piece to the puzzle. And with Zhurong's findings, we now know that the ocean story is not just speculation. It's a real chapter of Mars's history still waiting for its conclusion. Comparison with other missions, Mars has been a target of exploration for nearly half a century. NASA's Viking missions of the 1970s were the first to land successfully, but their tools were primitive compared to today's standards. They detected a barren landscape with little sign of life, leaving more questions than answers. Decades later, rovers like Spirit, Opportunity, Curiosity, and Perseverance transformed our understanding, revealing chemical traces of water and even organic molecules. Yet, none of these missions directly confirmed shorelines. Most relied on orbital images or chemical data to make inferences. That's where Zhurong stood out. With its ground-penetrating radar, it provided the first on-the-spot geological evidence of structures consistent with ancient coasts. This gave the Chinese mission a unique role in the global scientific conversation. NASA's Curiosity and Perseverance focused on different environments, such as ancient river deltas and lake beds. These regions show signs of water, but they don't tell the same sweeping story of oceans. Zhurong, by contrast, explored Utopia Planitia, a suspected ocean basin, and brought back results that strongly reinforced that hypothesis. The collaboration between findings is what makes the science so exciting. Each rover adds to the mosaic of Mars's past. NASA's missions highlight localized watery environments, while Zhurong paints the picture of a global-scale ocean. Together, they create a fuller vision of a planet that was once far more dynamic and habitable than it seems today. In this way, Zhurong didn't compete with other missions. It complemented them. By combining its results with decades of NASA data, scientists are now closer than ever to solving Mars's water mystery. The impact of the mission for China's space program for China, the Tianwen-1 mission, was more than just science. It was a declaration. By landing Zhurong successfully, China became only the second nation in history to operate a rover on Mars, achieving in one attempt what took others decades of trial and error. This was a leap in national prestige, technological independence, and strategic presence in deep space exploration. Unlike earlier missions that relied on international navigation or communication systems, Tianwen-1 was managed entirely by China. The success proved that the country could chart its own course in interplanetary exploration, from launch and navigation to landing and long-term rover operations. It was both a scientific and political milestone. Zhurong also laid the groundwork for future ambitions. The mission demonstrated China's ability to conduct complex operations, paving the way for upcoming plans such as a Mars sample return mission in the early 2030s and even long-term goals of sending humans to Mars. Each success builds confidence and expertise, moving closer to those larger milestones. For the global scientific community, China's arrival in Mars exploration brought fresh competition, but also valuable collaboration opportunities. With more nations actively studying the red planet, the pace of discovery accelerates and the range of perspectives broadens. Zhurong's data, shared in scientific papers, contributes directly to humanity's collective understanding of Mars. The mission proved one more thing. Exploration of Mars is no longer the domain of a single nation. It is becoming a global endeavor, with China now firmly among the leaders shaping the future of space science. The future of Mars exploration. While Zhurong's mission ended in 2022 after collecting data for nearly a full year, its discoveries set the stage for what comes next. Mars exploration is entering a new era, one where multiple nations and private companies race to uncover its secrets. Each mission builds upon the last, refining strategies and sharpening the search for life. NASA is currently focused on its Mars sample return project, which aims to bring pieces of Martian rock back to Earth. Though originally planned for the late 2020s, delays may push the timeline into the 2030s. If successful, it could finally allow scientists to analyze Martian material with the full power of Earth's laboratories. China, inspired by Zhurong's success, has its own plans for a sample return mission around 2033. This mission, if achieved, would be another giant leap forward, potentially bringing back soil and ice from regions linked to ancient oceans. Alongside this, both NASA and China are studying the long-term possibility of sending humans to Mars, though such missions remain decades away. Meanwhile, orbiters and rovers continue to map, scan, and dig. Perseverance explores an ancient river delta, Curiosity climbs the slopes of Mount Sharp, and European missions aim to join the effort soon. Each adds new layers of evidence, narrowing down where and how life might have once existed on Mars. The future is not just about science, it's also about survival. If humanity ever hopes to become a multi-planet species, the lessons from Zhurong and others will shape how we adapt to Mars' harsh environment. The discoveries of water, ice, and potential habitability are not just academic. They may one day be the lifeline for explorers who step onto Martian soil. Conclusion, with suspense. Zhurong's mission may have lasted less than a year, but its impact will echo for decades. In that short time, the rover revealed 3 discoveries that forever changed how we see Mars. Evidence of ancient shorelines pointing to vast oceans, hidden reserves of subsurface ice offering both clues and resources, and signs of geological activity that suggest the red planet may still be more alive than we thought. Each finding doesn't just add knowledge, it reshapes the narrative of Mars's history. The picture that emerges is of a world once vibrant, sculpted by waves, tides, and rivers, its coasts alive with potential. Beneath its frozen deserts, Mars still guards vaults of water, remnants of a wetter age, and deep underground, subtle movements hint at processes still unfolding. Far from being a dead planet, Mars tells a story of transformation, survival, and mystery. Yet, the greatest question remains unanswered. Did life ever emerge there? If ancient Martian beaches were as rich in chemistry as Earth's, could they have nurtured microbial ecosystems? And if so, might traces of that life still lie buried under ice or soil, waiting for us to uncover? The search is far from over. With upcoming sample return missions and future explorers preparing to set foot on the red planet, we are closer than ever to solving the riddle. Every new mission adds another piece to the puzzle, bringing us one step nearer to answering whether we are alone in the universe. Zhurong may have fallen silent under layers of dust, but the echoes of its discoveries continue to speak loudly. They challenge us to keep exploring, to dig deeper, and to follow the trail of water that once shaped Mars. Because perhaps, just beneath the Martian soil, lies the most profound truth of all, that life, even in the harshest of worlds, finds a way. Zhurong may have fallen silent beneath layers of Martian dust, but its discoveries still echo across the scientific world. Ancient oceans, hidden ice, and hints of activity remind us that Mars is far more than a frozen desert. It is a world with stories still untold. The question now is not whether Mars once had water, but whether it once had life. And if traces of that life remain, buried just below the surface, they may be waiting for us to uncover. Because in the end, exploring Mars is not just about another planet, it's about understanding our place in the universe.